Vijay reports.
Yeah. We just now wrote to CSRM. We check up. Yeah. Possibly we have it tomorrow. Okay. Good morning. Yeah. Any questions? So as we decided last week, we'll have the lab class at 3:30 p.m. today. Okay. I sent a mail also about that from the model. Just wait for a minute. Yeah, some students have a class in the head slot, which is there up to 3:15 or so. That is the reason we are pushing it to 3:30. I'm not sure how many students have the class in the head slot. So we'll meet at 3:30 today. We'll discuss. If required, we'll change it back to 2:30 if all of you agree. That we'll discuss in the afternoon. But today we'll meet at 3:30 only because I already fixed up some other meetings before 3:30. Yeah, I think it's Utkar who requested for this change. So if others don't have any class, no, because all others are supposed to be free in the P slot, right? And we normally take only about half an hour to 45 minutes for the lab class, not more than that. Okay. No, if required, you can go till 4:30. So we'll start at 3:30 and continue till maximum 4:30. Okay. Okay, let's get started. We'll just bring the screen. There are no other questions. Let us quickly go through what we are discussing in the last class at the end. So we are discussing this parity-based method for error detection. There are two cases where we'll be interested in using this parity-based method for error detection. One is when we send the data from one system to another system, right? And another one is where we store the data in the memory, and the data that we read should be same as the data that we have written into the memory, right? So this parity method is also used in the memory systems, mainly to detect if there is any error. The simple parity-based method can be used only for detection of an error in one of the bits either transmitted or stored in the memory. Okay. So in general, if there is a k-bit data where the k-bits are this x0 to x1, x2, so on up to xk minus 1, right? So we'll generate the parity bit using all these bits, and we transmit the parity bit or we store the parity bit also. And in the communication system on the receiving side, we again compute the parity bit from the received data bits, and we check whether this computed parity bit is same as the parity bit that's received. So if there is any one bit error in the data that is transmitted, then the parity bit that's generated at the receiving side will be different from the parity bit generated at the transmitting side. Sometimes there can be error even in the parity bit that's transmitted from the source to the destination. In that case, assuming that all the data bits are received correctly, But if the parity bit that's received is wrong, right, that also indicates an error, right? Uh, and we need to note that there is an error. Okay. Yeah. So we have seen the truth table for what is called the even parity scheme. That is the number of bits that are ones. If it is odd, then we'll make the parity bit to be 1, so that the total number of bits, including the data bits and the parity bit, is even. Okay. If already the number of ones is even in the data bits, right, then we'll make the parity bit to be 0. For simple case of k equal to 3, that's a 3-bit data that we are transmitting or storing. We have drawn the corner map and we derived the expression. It's seen that, right, we get an expression which cannot be simplified further, right? And because if you look at the corner map for this truth table, there are no adjacent ones in the corner map, and therefore the standard sum of products expression is same as the minimal sum of product expression for this problem, right? And it can be shown that the expression for this PG, that parity bit that's generated, can also be expressed in terms of the exclusive OR operation on all the data bits. This holds good for any number of bits. We can verify that. And on the receiving side, if the data that's received is, let's say, denoted by Y2, Y1, and Y0, so we compute the parity bit from these received data bits. That's called as a PC. And assuming that PG is received without any error, we check whether the PC is same as the PG. If both of them are same, then there is no 1-bit error in the data or in the parity bit. Sometimes the data bits might have been received correctly, but the PG itself might have changed, right? And in that case, again, the PC will be different from PG, right? And that will also result in the error. So if Z equal to 1, it indicates that there is a 1-bit error either in the data bits or in the parity bit. So this kind of a scheme is normally known as the single bit error detection scheme, and shortly it's called as the SED. Okay. And so please note that this method gives us only an indication that one of the bits, either in data or in the parity bit, has gone wrong, right? But it does not indicate which of these bits is wrong. Okay. So we cannot really correct that error, right? We can only get an indication that one of the data bits or the parity bit that's received or from the memory system, when we read it back, right, there is an error. Okay. And sometimes we have to ask for the retransmission of the data, and hopefully in the retransmitted data, right, the error is not there, because these are all kind of transient errors. Okay. But if you also want to correct this error that is occurred, right, then this scheme cannot be used. There are what are called the other methods known as the Hamming code based method. We'll not discuss it in this course. Maybe you'll study it in one of the other courses, right, either in your PDS course or maybe in the computer networks course, right? And this Hamming code method uses additional number of what are called check bits, which are similar to the parity bits, right? But the number of check bits required is more than 1, right? And typically for 8-bit data, I think if I am correct, it requires 4 check bits. If it is 16-bit data, it requires 5 check bits, and so on, right? So the overheads are high, but that will help you to correct 1-bit errors and also detect any errors that are there in 2 bits of either the data or in the check bits, right? And this Hamming code based method is referred to as the single bit error correction and double bit error detection methods, shortly called as the SEGDET. But the overhead that one has to bear with is large number of check bits, right, that need to be transmitted along with the data lines, data bits, or that need to be stored along with the data bits in the memory unit, right? And yeah, some question? Is there a question from anyone? Okay. Okay. So most of the simple memory unit. I think somebody's mic is unmuted. Can I request all the students to mute their mics? Unless you have a question. Okay. So this single bit error correction and double bit error detection are used, and that method is used wherever it's really critical to receive the data without any errors, or at least with no one bit error, which could be corrected, right? And similarly in the memory units, where it's very critical to have the data which is stored correctly and read correctly, right? So it's a question of how much price you are willing to pay in terms of additional check bits that are required, right? That decides whether you go for a single bit parity based method or this multiple bit based error correction and the error detection methods. Yeah. Any questions about this? Okay. If there are no questions, we'll go on to the next topic. With this, we close the discussion on the modular combinational logic circuits, right? Where you've seen basically encoders, decoders, multiplexers, demultiplexers, comparator, and then this parity checker and the generator. Now, just before we close this, please make sure that this is only for the even parity scheme. If you go for the odd parity scheme, the whole expressions will be different, right? Though the method is the same, right? So if you're really interested, please take it as an exercise to determine what is the expression for the parity bit, right? If you go for the odd parity scheme. Okay. Yeah. So if there are no questions, let's move on. Let me just check if there are any questions in the chat box. Okay, there's nothing. Okay. So let's move on to the next topic, right? Next, we would like to discuss the design of the arithmetic and logic unit for different types of data that we are interested in processing in a computer system. Okay. As you are aware of, broadly, there are two types of data that we'll be dealing with mainly in the numeric processing. That is the integer type data, which is basically the whole numbers, right? And the real value data, where typically there will be two parts, integer part and the fraction part. And when you use the scientific notation, we use what is called the exponent and matrix sum. We'll come back to the real value data representation a little later. Okay. First, we'll try to understand what is it involved in the representation of the whole numbers, and how do you represent unsigned numbers, and how do you represent the signed numbers. Okay. Some of you might have studied about this, right? So it may be slight repetition for some of you, but please bear with us. I just want to make sure that all of you have the background uniformly, because understanding these different representations of data is very, very important in order to discuss the design of the arithmetic and logic unit that forms the central part of the CPU. Okay. So first we'll look at the representation of the integers, and initially we'll focus on the unsigned integer representation. Then we'll move on to the signed integer representation. Okay. I think all of you are familiar with the conventional number system that we use, that the humans use, right? Which is the decimal system. As all of you are familiar with, the decimal number system that we commonly uses what is called a base, which is the base 10. What do you mean by this base 10? There are 10 different symbols, right? Symbols are denoted by these 0, 1, 2, so on. 9. So any number that we try to write is represented using these symbols, right? And typically when we say there is a sequence of symbols like say X is some 7, 4, 5, right? If somebody asks you what is the value of this X, which is given by the sequence of the symbols 7, 4, and 5, right? Then all of you would definitely answer it as 745, right? So basically the sequence of symbols where each of the symbols can be one of these 10 symbols in the base 10 system or the decimal number system, right, has a value, right? And the position of each of the symbols in the sequence also has a weight, right? So that's why these kind of systems are called the weighted positional number systems, because there is a weight associated with the position of a particular symbol in the sequence, right? And in general, if I denote the base as some B, right, and the position is indicated by some symbol I, right? So if I have some number X, which is represented by symbols X0, X1, and X2, so on, Xn minus 1, where there are n symbols, right? The value of this X can be expressed in terms of these symbols X0, X1, so on, Xn minus 1, and the base of the system and the position of the symbol in the sequence, right? We can easily verify that. So the value of this number X, which is represented by the sequence Xn minus 1, X2, so on, X1, X0, right, is given by Xi multiplied by B power I, right? So in the decimal number system, B is 10, right? Let's say for the illustration, we look at the case n equal to 3, right? So if X is denoted by this 745, right? We know that the weight of this position is 10 power 0. The weight of this position is 10 power 1, right? The weight of this position is 10 power 2, right? So that's how we get the value of this X as 7 multiplied by 10 power 2 plus 4 multiplied by 10 power 1 plus 5 multiplied by 10 power 0, right? And this you can extend it for any value of n, right? And once the sequence of symbols is given, right, then the value of that sequence of symbols is derived from this expression, right? So the decimal number system that we commonly use is a weighted positional number system with the base B, where B is equal to 10. I think all of you are familiar with the number systems which are actually not weighted positional number systems, as you people are aware of, right? If you look at the Roman number system, right, where the set of symbols that are used to specify a number in the Roman number system starts with I, which has got a value of 1, and P, which has got a value of 5, then X, which is a value of 10, right? Then L, right, which has got a value of 50, right? Then C, right, which has got a value of 100, right? Then D, which has got a value of 500, if I'm correct, right? And M, 1000, right? So one has to use these symbols to specify a number in a Roman number system. So if I have, let's say, some number Z, right? If we give the sequence of the symbols for this as this, right? All of you know that the value of this number Z is 8. But how do you get this? You just take the value of each of the symbols and then simply add them, right? So there is no weight associated with the position of the symbol in this Roman number system, right? And actually it's a little complex system, right? Let's say if I have Z as I followed by V, right? All of us know that this stands for 4, right? Whereas if it is v followed by I, then it's 5 plus 1, right? So it follows some set of rules, right, to derive the value of the number that's represented as the sequence of symbols, right? So the Roman number system is an example of a number system which is not a weighted positional number system, right? But the decimal number system, which all of us are familiar with, right, is a weighted positional number system. And one can actually use number systems which are other than the base 10, right? So if we use base equal to 8, right, we refer to it as the octal number system, right, where the symbols are going to be only from 0 to 7, right, and the weight of a particular position I is given by 8 power I, right? And one can also have the base 16 systems, which all of us are, I think, which some of you may be familiar with, right, which is called the hexadecimal number systems, right? And there are 16 symbols in this, 0, 1, so on, 9. Then we use the first 6 alphabet letters of English, A, B, so on, F, right, to form a set of 16 symbols. And the value of A is 10, the value of B is 11, and so on. The value of F is 15. And here, the weight of a particular position in the hexadecimal system is given by 16 power I, right? So typically, we denote the base of the system with the prefix here, right? So if I say X is, some number X is given in terms of, let's say, 723, right? If you don't specify any base, then normally we assume that it's a base 10 system, right? Or we specify the base of this system with the prefix, right? So in this case, it denotes that X is a number which is represented using the octal number system, right? And all the symbols in that sequence have to be in the range 0 to 7, right? Sometimes you may have the same sequence, right, where the numbers correspond to the hexadecimal system, right? Then the weight of the position will be different, right? So the base of the system has to be specified if the base that we are dealing with is something other than 10. Normally for the base 10, we don't specify, right? For other bases, we specify, right? But anyway, for most of the discussion that we'll be interested in, right, we are dealing with the decimal number systems, right? At some point of time later, right, we'll be seeing that the hexadecimal system will also be used for the sake of the convenience. We'll come back to it later. Okay. Yeah. So this is only for the way the numbers are represented in a system that the humans are familiar with, and where it's convenient for the humans to do the manipulations or the processing of the numbers. But when we want to represent the numbers in the computer system, the only symbol that we have is the bit, right? So the bit will take the value 0 or 1. Actually, that's where the bit, the name has derived. The bit stands for the binary digit, right? So it takes only 2 possible symbols, right? So the binary number system is a system with the base equal to 10, right? Where the symbols are going to be only 0 and 1, right? So if I have n equal to 4, right? So X can be any sequence of zeros and ones, right? Let's say it is 0, 1, 0, 1, right? And if you denote the base of the system, right? Then we can determine the value of this X that's represented by the sequence of bits, right? Which you can easily verify that, right? This has got a power of the weight of 2 power 0. This has got a weight of 2 power 1. This has got a weight of 2 power 2, weight of 2 power 3, right? So 8, 4 to 1, right? So what is the value of this x here? You can easily verify that. In this case is 4 multiplied by 1, right, plus 1 multiplied by 1. So that is equal to 5, right? So basically what we are doing is that we are getting the value of x as summation xi to power I equal to 0 to n minus 1, right? Only thing is the xi can take either 0 or 1, right? And the number of bits that are used to represent the x, right, will determine the value of this n. Okay. So it's basically extension of the weighted position number system. From base 10 in the decimal system, we go to the base 2 in the binary number system, right? And every bit is represented in terms of the electrical signals, right? Either 0 volts for the 0 bit, right? And plus 5 volts for the bit 1, okay? And the other interpretation that we give is the 0 is associated with the true, and 0 is associated with the false, and the 1 is associated with the true, right? That's only for our interpretation. But if you're going to represent the numbers, right, then the numbers are going to be represented only using the sequence of bits, right? And right now we are talking about what is called the unsigned integer system. We'll come back to the signed integers a little later, right? Actually, all of you might be familiar with the data type in the C language, right? Where you can declare a variable as unsigned integer. Actually, there are multiple types of unsigned integer, right? You can simply have unsigned byte or unsigned short integer, or you can just have unsigned integer, right? So what are these three different data types you have in the C programming language? When you say unsigned byte, right, that indicates that the variable can be represented using maximum of 8 bits. Sorry, the numbers are represented using 8 bits. When you say unsigned short, right, the value of n is 16, right? And if you simply say unsigned int, n is equal to 32, right? So what does this mean? Why do you have to specify the size of the integer value here? That is, what is the number of bits that are required? Why do you have to specify that? As you'll be seeing later, right, that plays a very important role in terms of the storage that's required, and also in terms of the circuit that needs to be used, because for different values of n, you may use a different circuit, right? And the time taken to perform the operations also will be different. So typically for the smaller value of n, the time taken to perform any arithmetic operation will be less compared to the time taken for performing the operations for larger value of n. Okay. So now let's see what is the range of values for each of these cases that can be represented. As we'll be quickly seeing, right, there is only always a finite range of values that can be represented using a particular representation, right? So if n equal to, let's start with n equal to 4, right? What is the range of values the number can have? Let's say I'm denoting a number with some symbol x, with a variable x, right? What is the range of values this x can take, right? So you can get that by looking at what are the possible sequence of bits that we can have. We can have the sequence of bits starting from 0, 0, 0, so on. Sorry, all ones, right? So the smallest magnitude of the number corresponds to when all the bits are 0, and the largest magnitude corresponds to when all the bits are 1, right? What is the value of this bit sequence? You can easily verify that it's 0, right? What is the value of this bit sequence? You can easily verify that it is 50, right? And can you express this 15 in terms of 4 here? Again, you can easily verify, right? It's 2 power 4 because 2 power 4 is 16, right? So the largest value that can be represented using 4 bits is 2 power 4 minus 1. And in general, we can represent the range of values for n-bit unsigned integers as 0 to 2 power n minus 1. Okay. So for n equal to 8, it is 0 to 255. For n equal to 16, you can easily verify that it is 0 to, yeah, you need some calculator. Yeah, what is 2 power 16? It is of the order of 65,000, right? What exactly is the value? Yeah, you can verify. If I'm correct, it is. Let me also just check that. It's actually 2 power 16 minus 1. Right? I hope this number is correct. Yeah. Okay, you can easily verify. Right? What does that mean? If you declare a variable as an unsigned byte, that variable can take values in the range 0 to 255, and it is your responsibility to make sure that the variable will not be assigned any larger value. And if you declare a variable as unsigned short integer type, that variable can be assigned a value in the range 0 to 2 power 16 minus 1, that is 65,535. So basically, any value beyond this 2 power 16 minus 1 cannot be handled by variables of the unsigned short integer type, right? And if you go for n equal to 32, right, which is 0 to 2 power 32 minus 1, I'll give you approximately, this is, as you can easily verify, right? Because as we were discussing earlier, 2 power 10 is 10 power 3, 2 power 20 is 10 power 6, 2 power 30 is 10 power 9, right? So 2 power 32 is 4 multiplied by 10 power 9 approximately, right? What does this mean? I can represent the numbers from 0 to approximately 4 billions, right? Because 10 power 3 is kilo, 10 power 6 is million, right? And 10 power 9 is billion, right? So as long as we are interested in the numbers only from 0 to 4 billion, right? Then we can use this we can use this 32-bit data type called the unsigned integer. And if you are interested in for any application where the value of the variable can take a value, or the variable can take a value beyond this, that is greater than this 4 into 10 power 9, right? Then this representation will not be adequate, right? So that's why many of the 64-bit process nowadays will support n equal to 64 as well, which means that you can go from 0 to 2 power 64 minus 1. Only thing is, in the programming language, you should introduce a corresponding variable type, right? No, it can be something like a long integer, double integer, and so on, right? That's not yet standard, right? So if one wants to have an unsigned integer variable of 64 bits, right, then one has to have a suitable data type. And in that case, the range of values for the variable can be from 0 to 2 power 64 minus 1. Okay. So what you see is that the type of variable that we use, the declaration that we use for variable will be implicitly having a predefined range of values that variable can take, right? But when you go for a smaller range, if you are very sure that, right, the range of values for that variable will not go outside the range of values that representation can take. Okay. So when you are writing the program, you have to be sure of what is the range of values that variable can take. Of course, you can always say that I'll go for any variable n equal to 32, right? But as I said, if you're dealing with only small range of numbers, right, that will be leading to unnecessary wastage of storage and also unnecessary wastage of time in processing the data. If, let's say, if all your values are of interest or in the range 0 to 55, right, by using n equal to 32, right, you'll be unnecessarily wasting a lot of storage as well as the computational time, right? So one can choose the appropriate data type, right, depending on the range of values that the variable that you are interested in dealing with is likely to take. Okay. Are there any questions? So I wanted to be clear about how the unsigned integers are represented in the binary system, right? And what is the range of values the numbers can take depending on the number of bits used to represent the numbers. Okay. Now we'll introduce another term that will be interested in, what is called the resolution or precision of the number system, right? And what is the definition of this resolution of the precision? The difference between two successive numbers that can be represented. Right? So let's say if I take n equal to 4, let's say if I take some sequence 0, 1, 0, 0, right? What is the next number I can represent? It is 0, 1, 0, 1, right? So the value of this 0, 1, 0, 0 is 4. The value of this 0, 1, 0, 1 is 5, right? So the absolute difference between the two successive numbers in this case is actually 1, right? And actually for all the integer representations, right, we'll see that the resolution is fixed or the precision of the number system is fixed, that is 1. But when we come to the real value representation, right, we'll be seeing that the precision can change depending on the type of the representation that's used, right? Actually, that's where the floating point number system comes to the picture, right? Then depending on the range of values that we are dealing with, the resolution or the precision with which we can represent the numbers can be varying, right? So we'll come back to the that point later, right? For the time being, I just want you to note that the term here, the resolution or precision, refers to the absolute difference between two successive numbers that can be represented in a number system. For all integer representations, that precision happens to be only 1. Okay, so the precision for integers, irrespective of whether we are talking about unsigned integers or later signed integers, or what the value of this n is, right? So for integers, the precision is going to be 1. I just want to make a note of this. We'll come back to this precision when we talk about the real value data, right? Because there it's going to be a little different. Okay. Yeah. Now, what you have seen is that we are able to represent only non-negative values here in this system. That's why we are calling it as the unsigned integers, because we are not talking about the negative numbers at all, right? When we are dealing with this unsigned representation, right? So when n is equal to when n is taking some value, right? All those n bits, right, are used to represent only the magnitude of the number here, and that magnitude can range from 0 to 2 power n minus 1. Okay, so now we'll see what is it we have to do, right, when we have to deal with the representation of signed integers. Okay. So now we want to deal with numbers where the numbers can be either positive numbers or negative numbers, or of course it can also be 0, right? In the decimal number system, we put a symbol that indicates, right, whether the number is negative or not. So we put a dash before the number. That dash indicates that that number is a negative number. And normally for positive numbers, we don't use any symbol. So if there's no dash before the symbol or before the number, then it is interpreted as the positive number, right? But unfortunately, there is nothing like a dash in the binary system, right? So we had used one of the bit values, that is 0 or 1, to represent the sign information, right? And because the sign can take either positive or negative, right? We'll be seeing that we'll use one of the bits to denote the sign. So that will be called as the sign bit, right? And when you use totally n bits, one bit will be taken to represent the sign bit, and the remaining n minus 1 bits will be used for the magnitude. Okay. And typically this sign bit will be the most significant bit. Why do we call it as the most significant bit here? What is the most significant bit? If you're talking about some n bit number, right? So what is the most significant bit? So let's just look at here. Yeah. Let's say I have x, which is denoted by xn minus 1, xn minus 2, so on, x naught, right? Which of these bit positions has got the maximum weight? Obviously, the position corresponding to the n minus 1, right? So this is referred to as the most significant bit position, and this position, 0th bit position, is referred to as the least significant bit position, because it has got the least weight, right, for that position. Okay, so the leftmost bit is the least significant bit, the rightmost bit is the most significant bit in the unsigned integers, right? And in the case of signed integers, also we'll use the most significant bit to denote the sign bit, right? And the other bits to represent the magnitude. Actually, there are different forms of this representation of the signed integers. The simplest form is what is called the sign magnitude form, right? Which follows this notation where there is a sign bit and there are n minus 1 bits for the magnitude. Okay, so let's again take some n equal to 4, right? So if the value of some variable x is, let's say, plus 5, right? So the sign bit will be 0 to indicate that it's a positive number, right? The remaining bits are used to represent the value of this number, that is 5, right? We can easily verify that it is 101, right? So this is the sign bit, right? And the remaining n minus 1 bits in this case collectively indicate what is the magnitude of that number. So if x is minus 5, right, what will change here? The sign bit will change from 0 to 1, but the magnitude bits are the same, right? So basically what we are saying is that the rightmost bit, sorry, the leftmost bit here, right, will be the sign bit, right? And that will take a value of 0 for all the positive numbers. And if it is 1, then it indicates the negative number. The remaining bits indicate that indicate the magnitude of that number, right? So let's take another number. Let's say if it's plus 6, right? It is 0, 1, 1, 0. or if y is minus 6, right, it is 1 followed by 1, 1, 0, right? Then obviously there are going to be questions, right? What happens if I have all zeros, right? Let's say this corresponds to some variable z, right? So as per our definition, we should call it as plus 0 because the sign bit is 0, it's positive, right? And magnitude is 0. And if I have this bit sequence 1, 0, 0, 0, right? As per our definition, right? This should be called as minus 0. But normally in the number system that we use, right? We don't associate any sign with the 0, right? So we don't have minus 0 and plus 0 in the decimal number system that we normally use, right? But when we talk about the binary representation of the numbers, right? If you are using sign magnitude form, right, then there'll be two different representations for the 0, right? Called the positive 0 and negative 0. So what is the range of values now for an n-bit number in sign magnitude form? So what is the maximum positive number that one can have in this case? So we have 0. Then on the positive side, we can have the values from 1 to so on, right? So if n equal to 4, right, what is the maximum value that you can have? You can verify that it is 7 because the maximum value is given by the combination of 0, 1, 1, 1, right? And on the negative side, it is minus 1, 1, 1, right? So this is plus 7, right? And if it is all ones, right, it is minus 7, right? So we see that now this number line is having the positive side and the negative side, right? So we can represent the numbers from minus 7 to plus 7, right? So the number of combinations that's possible is 16, right? But the unique values that we represent here is 15 because the 0 has got two different representations. Now, can we generalize this range of values for any n bits, right? So as you can verify that, right? This is 7 is 2 power 3 minus 1, minus 7 is minus 2 power 3 minus 1, right? And we can generalize this for any n bits as minus 2 power n minus 1 minus 1, 2 power n minus 1 minus 1. So the largest positive value that we can represent is 2 power n minus 1 minus 1, right? And the negative of that number is the smallest number that we can represent, right? Or the negative number is the maximum magnitude is the 2 power n minus 1 minus 1, right? But please remember that when I have n bits, right, the number of combinations that's possible is 2 power n, right? But because 0 has got two different representations, right, the total combinations will be still 2 power n, right? But the unique values that we represent is one value less than 2 power n. Okay. Now, can we come up with the expression for x in terms of the elements of x? That is, if I have xn minus 1, xn minus 2, so on, x1, x0 to represent this x, if x is a signed integer that's represented using the sign magnitude form, what is the expression for the value of x? Yeah. What is the value of x? Actually, you can see that I can borrow the expression from the expression for the unsigned integers, because what is the magnitude represented by here? The n minus 1 bits, right? And how do I get the value of that magnitude? It is similar to the unsigned integer representation, right? So it will be xi 2 power I. Only thing is I can range from 0 to n minus 2 now. Earlier it was 0 to n minus 1, right? In the case of the unsigned integers. because here the magnitude is represented by only n minus 1 bits, and those positions are 0 to n minus 2, right? So this will give the magnitude of this x. Then how do I get the sign of the x? Sign is represented by the bit xn minus 1. If xn minus 1 is 0, then this number is positive. If xn minus 1 is 1, right, then this number is negative, right? So we can write it as minus 1 to the power xn minus 1, right? Because if xn minus 1 is 0, right, then whole of this term will be 1, right? If xn minus 1 is 1, right, then the whole of this term will be minus 1, right? So we can represent the value of x as minus 1 to the power xn minus 1, where xn minus 1 take either 0 or 1, right? And the magnitude of that number is given by the remaining bits, right? That is summation xi to power I, right? So given the bit sequence, once I know that I'm using the sign magnitude representation, right, then I can get the value of the x using this bit sequence, and noting that it's a sign magnitude representation. Okay. So this is the simplest form of representation of the signed numbers, signed integers, right, in the sign magnitude form. But as we'll be quickly seeing, this representation is not really convenient to perform the arithmetic operations, right? And the circuits that we need to implement will be complex when we use this sign magnitude. Just 1 minute. Okay. So let's say if I want to perform simple addition operation, how do I perform the addition operation? Let's say if I want to perform the addition operation on the unsigned integers, what is it we can do? Let's take, let's say z equal to x plus y, right? Let's see if all these numbers are represented using 4 bits, right? Let's say x is 0, 1, 1, 0, that is 6, right? And y is 0, 0, 1, 1, right? That's 3. So if I want to get z equal to x plus y, right, we can easily verify that if I just perform the bit by bit addition here, we'll come back to the details of the operations and the circuits to do that, right? So I just take like what we do in the case of the addition of the decimal numbers, right? We start with the least significant position and then move towards the left to the more significant positions, right? And when we add the two symbols in a particular position, there can be a carry out of this, right? So in this case, when you add 0 and 1, it will give me 1. When we add 1 and 1, it will give me a sum of 0. Then there will be a carry to the next bit position, right? Like when we add the decimal numbers, if I add two decimal number digits, right, the sum can be less than 10 or greater than 10 or greater than or equal to 10. Whenever it's greater than or equal to 10, there will be carry into the next position, right? In the same way here, right, there is a carry into this next bit position here. And when we add this also, we'll get a 0 here, and then we'll get a carry here, right? And finally, when we add this, it is 1001. You can easily verify that this corresponds to 9, right? So as we've seen later, if I'm interested in adding two numbers which are represented using unsigned integer representation, the addition can be simply carried out by performing the addition of the bits in each of the positions, right? And then realizing the sum. So the circuit turns out to be very simple, and our arithmetic operation also turns out to be simple. It is actually similar to the manual addition method that we do on the decimal numbers, right? Except that we will be doing it in the on the binary representations of the numbers. Okay. I want to think about if I have two numbers which are in the sign magnitude form, right? That's what we are talking about here. Let's say x equal to plus 5 and y equal to minus 3, right? If I get the corresponding corresponding representations of +5 and -3, which you can easily verify that 0, 1, 0, 1, right? And this is 1, 0, 1, 1, right? Can I just add these bit sequences and then get the value of Z as 2, right? So I'm going to leave it as a small exercise for you to take different combinations of values for this X and Y, right? And you try to add them. You first get their representations, then try to add them, and then see whether the resultant bit sequence is going to correspond to the values of Z that's required. And if you want to perform the subtraction operation, how one can do that, right? So you'll quickly realize that, right? You want to perform the addition and subtraction operations on the sign magnitude form of the signed integers, right? It turns out that is a fairly complex sequence of operations that we need to carry out. Therefore, this sign magnitude form is not really suitable for performing the arithmetic operations on the signed integers. Okay, so I just want you to take it as an exercise, right, to perform the addition and subtraction operation on this X and Y, right, for these values, and also you can take some other values, right, and then check how you can perform the operations on the bit sequences and then get the correct value for the Z, right? So Z can be either X plus Y or Z is equal to X minus Y. So I want to simply perform either addition operation or the subtraction operation on the two numbers, right? If I'm given the binary representations of the two numbers X and Y, how do I get the representation for Z, which will correspond to the value of the sum of the X and Y or the difference between the X and Y. Okay, so take this exercise. We'll continue the discussion in the class tomorrow. Okay, maybe I'll stop at this point. Are there any questions? Yeah. So I want you to make sure that you're clear about the representation of the unsigned integers and the representation of the signed integers in the sign magnitude form before you come to the next class. Okay. Looks like there are no questions. If there are no questions, I think we'll stop at this point and close the session. Okay. Thank you. Question from Shanti is, how is the attendance taken for this course? Right now, I am not marking the attendance. I hope that this will not make the people to skip the classes. Okay. Yeah, because we are not figured out the mechanism to take the attendance on this Google Meet yet, right? We'll try to figure out if there is a way to take the attendance on the Google Meet, right? We'll try to do that. Okay. Yeah. Don't attend the classes just for sake of attendance, right? Okay. Yeah. We'll close the session now. Thank you. We'll meet in the afternoon at 3:30.